In this video, we will be covering how to solve rational inequalities. We're in Chapter 3, Section 6, and it's designated 3.6b because we split this section. The first section we talked about solving polynomial inequalities. We learned the test point method, and that's what we're going to be continuing with in this section. Now, this guided note set that you printed actually starts with this page that is a review of 3.5 rational functions. We're not going to cover this together in a video. If you're in one of my classes that meets in BBCU, then this is one of the activities that we will cover on a day that we meet in BBCU. If you're in one of my Connect classes and we do not meet in BBCU, go ahead and try to fill in that review. If you have questions, contact me by email. I'll be happy to go over it with you or to send you a key. So back to solving rational inequalities. Like I said, we already learned how to do this basically using the test point method in 3.6a with polynomial inequalities. The major important difference between polynomial and rational inequalities is that with rational inequalities, I have values that are undefined in my domain. So I've kicked them out of my domain. So I'm not just interested in finding values where the function is equal to 0, but I also have to be aware that I have places where my function is undefined. That's a small difference, but it is significant. We do need to pay attention to what that does to some of our endpoints. Okay, so our three basic steps for solving these inequalities. First, we're going to write the inequality so that 0 is on one side. So we set it to 0, just like we did with polynomial inequalities. We want to make sure we have a single ratio in lowest terms on the other side. Now this is new because we didn't have ratios with our polynomial inequalities, but we're going to want to make sure that we've got it set to 0. For example, right here, our first example, set to 0, a single ratio, and that single ratio is in lowest terms on the other side. The second step is going to be to find all the zeros in both the numerator and denominator. Now this is where it's important, this important distinction for rational inequalities comes into play. Any zeros that come from the denominator represent a vertical asymptote, and that's a place where our function is undefined. So it doesn't matter whether my inequality symbol includes values of 0 or doesn't include values of 0 for these zeros. If they come from the denominator, they're places where the function is undefined, so the function can never be equal to that. Then we find zeros from the numerator, the top part. They represent places where our function value is 0, or the y value equals 0. These are the zeros that could be included in our graph. For these zeros that come from the numerator, it matters whether our inequality symbol is or equal to, or just greater than or less than. So once we have set it up correctly, we found all of our zeros, whether it represents a place where the function is undefined or equal to 0. Our last step is to place all of those zeros on the number line, all the zeros, whether it's an undefined or a value of 0, and test a point inside each of the resulting intervals. So let's do this first example together. We're going to find the intervals that satisfy this inequality. We want to know where this rational expression is greater than or equal to 0. So I've already got number 1 taken care of. It's written correctly. Set to 0, a single rational expression on the other side. Now we're going to find all of those zeros from my numerator and denominator, and I'm going to place them on a number line. Let's see. We've got zeros in our denominator first. These are places where my function is undefined. We're going to say, well, my denominator is x squared minus 1. That's difference of squares. Difference of squares factors out to give me conjugate pairs. So I get values for, where would that be 0? Well, it's 0 at -1 and at 1. And this is places where my function is undefined because those are zeros that come from my denominator. Then I look at my numerator and I say, okay, what would make x plus 3 equal to 0? Well, I solve and I get negative 3. This is a place where the function value is 0. So my function value is 0. It comes from the numerator, so it's an actual 0 of my function. It's a place where that function is equal to 0. So I have 3 values to place on my number line. I have negative 3, negative 1, and positive 1. That should have been in my circle. Always go from least to greatest on your number line. I have negative 3, negative 1, and positive 1 from least to greatest. I have created 3 boundaries, which gives me 1, 2, 3, 4 intervals to test. And unlike my polynomial inequalities where I could kind of use the shape of the graph, the end behavior, behavior of the zeros to predict what's going to be where, we don't want to take the time to graph this function. So we want to pick values that fall in each of those intervals and test to see if everything in this interval is positive or if everything in this interval is negative. And then we want to go through and do with each of those. Now, as I place these boundary points on my number line, I want to pay attention. Is this a value of 0 for the function, or is this a place where the function is undefined? Well, the zeros that come from my denominator are places where the function is undefined. So I'm going to remind myself of that. And the zeros that come from the numerator are placed where my function value is 0. So I'm going to remind myself of that. Now let's go through and let's do test points within each of these. My ends, you know, I always just go big. So I'm going to do negative 100 and positive 100. In behavior, it's either going to be heading way up or heading way down. So I just pick something that's way out there so I don't have to worry about, is it close or is it for sure? 0 is always easy. 0 fits here. And what's between negative 1 and negative 3? Well, the simplest will be that integer negative 2. So I'm going to check for these values to see what would happen in that rational expression. So I'm going to say, for example, let's just do this one because 0 is easy. If x is equal to 0, what happens in this expression? Does it give me a value that is positive or does it give me a value that is negative? Well, if x were equal to 0, my numerator would be 0 plus 3, and my denominator would be 0 squared minus 1, which gives me 3 over negative 1. So I have a positive over a negative, and a positive divided by a negative is negative. So that interval is negative. This one right next to it, I have to do a little bit of work for. If x were equal to negative 2, and I plug that into my rational expression, I would have negative 2 plus 3 as my numerator, negative 2 quantity squared minus 1 as my denominator. So my numerator comes out to be a positive 1. That positive part is what's important. My denominator would be 4 minus 1, which is also positive. And a positive divided by a positive is positive. Specifically, it would be 1 over 3, which is a positive 1/3, but we don't care about the value. We care about the sign. Okay, so now my ends, I'm left to my ends. Let's go ahead and do this end where x is a positive 100. What if I plug in a positive 100 for x? I could have just have easily done a positive 2 or a positive 10 or a positive million or a positive 7. Anything greater than 1 is going to work here. But 100 is usually easy. So I plug that into my rational expression, and I get 100 plus 3 over 100 squared minus 1. Well, my numerator is 103. That's positive. My denominator is 100 squared minus 1. That's huge and definitely positive, right? So positive divided by positive. That interval is positive. All values will be there. What about this other end? What if x were something negative large, or at least bigger or smaller? A smaller value than negative 3 that is further out in this negative direction than negative 3. All right, plugging negative 100 into my expression, I have negative 100 plus 3 over a negative 100 squared minus 1. Well, a negative 100 plus 3 is definitely a negative value. In fact, it's negative 97, but we don't care about exacts. When I square this negative 100, it becomes positive, a 1 with 4 zeros after it, minus 1. So I've got a positive 10,000 minus 1, which is a positive 9,999. And I've got negative divided by positive, which results in a negative. Okay, let's think about what our inequality is asking. Our inequality is asking, where is this graph going to be greater than or equal to 0? Where are my function values greater than or equal to 0? Well, if this is my x-axis, we're looking for things that are up here or on the x-axis and worth a function value of 0. So greater than or equal to 0, I'm looking for positive values. And I get to include the boundary points where the function value is equal to 0. I can't include boundary points where the function value is undefined because those represent vertical asymptotes. They are not part of our graph. Okay, so this end is not included. This interval is. So from negative 3 to negative 1, I have x values or function values that are greater than or equal to 0. This boundary is included because it is a true function value of 0. This boundary is not included because this is a place where the function is undefined. The other interval that I'm going to include is this end that starts at 1 and goes to positive infinity. Well, positive infinity is always a curved parentheses. This boundary is undefined, so it has to be curved as well. Okay. For the next question, it says, what if? What if the inequality were rewritten and the only thing that changed here is this inequality symbol? Same expression, so all of my work is still the same, but now I'm interested in places where the function value is less than 0. Just less than, so I'm not going to include any boundary points, not even this negative 3, because I'm not interested in equal to. Less than are those negative intervals, so I'm interested in these two intervals this time. Oh, these two intervals this time. I pointed the wrong direction, right here. I'm interested in here, in this lower end, this negative most end, and the interval from negative 1 to 1. So from negative infinity to negative 3, or negative 1 to positive 1, those are the two intervals that satisfy this particular inequality, because that's my less than sign. So I'm interested in those negative intervals, and it's not or equal to. So I don't even include those boundary point values that would give me function values of 0. All right, let's look at the next page and work through that next example. This one says, again, to find the intervals that satisfy the inequality. This time, however, I am not starting with it set to 0, so I need to do some work before I ever get to the place where it's set to 0. I'm going to need to move that 1 over to the other side. So let's just start by doing that. Let's say we have 2x over x plus 1 minus 1. And then I'm going to have that still greater than or equal to 0. Well, I need to write it as a single rational expression, so I need a common denominator. My common denominator is anything over itself, so I'm going to use a well-determined 1. That's going to be that denominator x plus 1 that I need to multiply in. So I just multiply my negative 1 times x plus 1 over itself, and that allows me to write my rational expression with a single denominator. I start with that 2x and then I distribute my negative. So minus x minus 1 is now my numerator. And I want to combine like terms to simplify. Well, 2x minus x is x, and then I have minus 1 over x plus 1 greater than or equal to 0. This is the rational expression that I'm working with. So that's my step number 1 of my 3 steps back from the first page. First step was to rewrite the inequality so it's set to 0 and I have a single ratio in lowest terms on the other. Next, I'm going to find all those 0 values from the denominator and numerator and place them on the number line. Okay, so let's get our number line up there. You know what we're working with. And then we are going to look at our values that can be zeros. So from our numerator, we have x minus 1. So what makes that 0? Well, a positive 1 makes that 0. That comes from the numerator, so it's an actual function value of 0, Then from my denominator, I have that x plus 1. What makes it equal to 0? Well, a negative 1 would make that happen, but that's from my denominator, so that's a place where my function is undefined. It's never equal to that. I only have those two boundaries to place on my number line. I have positive 1 and negative 1. I go in order from least to greatest. Since I have two boundary points on my number line, that gives me 3 intervals where I need to test. 0 in the middle is always easy. For my large ends, I'm just going to use negative 10 and positive 10 this time to remind you that there's not a magic number there. I'm just picking easy values that I can plug in and tell pretty quickly what I'm working with. Okay, so these are my test points. I like to start with 0 because 0 is pretty simple. If x is 0, now remember I'm working down here with my altered expression. This is what I'm working with. If x were 0, my numerator would be 0 minus 1 and my denominator would be 0 plus 1, which gives me negative 1 over 1, which is negative. So every y value, every function value in that interval is going to be negative. Over here on the rightmost end, my x value is a positive 10. So if I plug in 10 for x here, that is 10 minus 1 over 10 plus 1, which gives me 9 over 11. Still positive. Not really concerned about the actual value there, just interested that it's positive. Okay, so our final test point we want to check is if x were negative 10, that's this leftmost end. Plugging it into my rational expression would give me negative 10 minus 1 over negative 10 plus 1, negative 11 over a negative 9. Don't really care about that actual value. What I care about is that a negative divided by a negative is positive. So every value in that interval is positive. All right, let's evaluate our inequality symbol. Our inequality is greater than or equal to 0. So I'm interested in these ends where we are positive. One thing I forgot to mark. Oh dear, one thing I forgot to mark. At positive 1, I have a function value of 0. At negative 1, my function is undefined. That helps me figure out exactly how to write these intervals. Well, I've got or equal to, so I get to include function values that are equal to 0. This function value is undefined, however. So this end is negative infinity up to negative 1 not inclusive, or this end is positive 1 to infinity and that 1 is included because that's a function value of 0. Let's look at that next example. Once again, we have to do a little work with our rational expression to get it set to 0, and then we're going to have to get that written as a single rational expression. So I'm going to move that 3 over, subtract it to get it over to the other side. My inequality part does not change. I've just subtracted 3 from both sides. And then I'm going to multiply by that well-chosen 1 that is my denominator I want to introduce, so that I can write this as a single rational expression with a single denominator of 2x minus 1. My numerator is going to be x plus 4, and then I take this negative 3 and I distribute it. So negative 6x plus 3. And then I combine like terms in my numerator. So my numerator, x minus 6x is a negative 5x. 4 plus 3 is 7. And then my denominator is 2x minus 1. And I'm interested in where this function, this inequality, is greater than or equal to 0. So that is what I'm working with. Now from this, I'm going to look at my numerator and denominator to discover what my boundary points are, where my graph is going to have either a vertical asymptote where the function is undefined, or it's going to run into that x-axis and create a boundary. From my numerator, I have the function values that are equal to 0. So I want to know negative 5x plus 7, where is that equal to 0? I move that 7 over, so I have negative 5x is equal to a negative 7. And then when I divide both sides by negative 5, I get x equals a positive 7/5. This is where my function value is 0, positive 7/5. Then I look at my denominator and I say, all right, well, what makes 2x minus 1 equal to 0? Move that 1 over and divide by 2, and I get x is 1/2. This is a place where my function is undefined because that comes from the denominator. I have 7/5, which is just a little bit bigger than 1. It's 1 2/5. And then I have positive 1/2 as my boundary values for this function. Well, 7/5 is the larger value. They're both positive. So I have positive 1/2, positive 7/5 on my graph. 2 boundary points, divided my graph into 3 intervals. I need to test a point in each interval. 0 does not go in the middle because these are both positive. So 0 is a test point I can use for this left end. I can use anything bigger than 1 2/5 over here for the right. Let's go ahead and do 10 again, I guess. And then I need something that fits in the middle. Well, remember we said 7/5 is 1 2/5. So 1 is going to fit. That integer 1 falls between 1/2 and 7/5. So those can be my test points. Let's go in and let's check these test point values. If I start with 0, just because that's my habit, I plug in 0 into my rational expression that I have simplified down here to. I would have negative 5 times 0 plus 7 over 2 times 0 minus 1. Now I know that anything times 0 is 0. So that gives me 7 over negative 1, which is negative. That's the important piece of that. Then for my middle interval, I'm suggesting a value of x as 1. So I plug that into my expression. I get a negative 5 plus 7 is positive 2. 2 minus 1 is 1. What matters with that is that both of those are positive. Over here in my right hand end, my rightmost interval, I chose 10. So that gives me negative 5 times 10 plus 7 over 2 times 10 minus 1. Well, that's a negative 50 plus 7. It's a negative 43. It doesn't really matter that it's a negative 43. What matters is negative. My denominator is 20 minus 1, which is 19. Negative divided by a positive is negative. Now, I want to point out that each of our examples have had alternating signs from one interval to the next. This is not always the case. So don't make that assumption that just because you know where one is, you know where the rest of them will fall. Okay, going back to look at my inequality symbol, I'm interested in intervals greater than or equal to 0. So I'm interested in my positive values. So once again, I need to say, okay, at 7/5, that function value is 0. At 1/2, my function is undefined. So that when I write the intervals that satisfy my inequality, I'm interested in this middle. I cannot include 1/2 because the function is undefined there. I have a vertical asymptote. But I can include 7/5 because that function value is equal to 0 and my inequality symbol says or equal to. All right, excellent. So let's look down here. We have 2 more practice problems. One is already set to 0 for us. One is not. I'm going to give us a little bit more space designated for the second problem because we'll need to do a little bit more work. I'm going to go through these fairly quickly because we've just done 3 together. So I'm going to talk through these fairly quickly. I encourage you to pause the video right now and see what you can do on your own, then come back to see what we do together. I got a little bit of a head start for us on number 1. Because this is already factored, I can see that from my numerator, I have the zeros -3 and +2. So those are function values of 0. From my denominator, I will have a 0 at -1. And because that's in the denominator, that's a place where my function is undefined. I just need to pick, test point values for each of these intervals. 0 would go here, 100 or a 10 or a 5 or something positive bigger than 2 goes at this end. Something negative past -3 goes at this end. And then a nice integer between -1 and -3, -2 will be an easy value to test. When I check my test points, for example, if x is 0, if I test that, I would have 3 times -2 over 1. That gives me a negative over a positive, so that interval, all of those values will be negative. If I check, let's do -100 together. If I plug in -100 into my expressions, that -103 is going to be negative. -100 minus 2 is also negative. -100 plus 1 is negative. This, a negative times a negative is a positive, but I'm dividing that by a negative, and that overall result is negative. When I plug in a -2, I have -2 plus 3 is 1. -2 minus 2 is a -4. -2 plus 1 is a -1. And that gives me a negative divided by a negative, so that interval is a positive. I'm not going to plug in and work through because I have confidence that you know how to do that. This end is a positive interval as well. Well, what am I being asked to look for? I'm interested in intervals that are less than 0 or equal to. These values are function values equal to 0. This one is undefined. So I'm interested in these negative intervals, the ones that would fall beneath the x-axis. So I've got -infinity up to -3, and I get to include that because it's or equal to, or, and then I want from -1 not inclusive because the function's undefined here, up to 2 included. Okay, our last example together from this section. It is not set to 0, so that is my very first step, is to set this to 0 by moving the 2 over and then multiplying it times a well-chosen 1. If you have, oops, that needs to be -2, less than or equal to 0. If you have not already paused and worked through this on your own, I really want you to do that to see how you can do without me leading you through step by step. Remember, when we distribute, we're distributing that -2. So that this is the rational inequality that we're working with. I'm going to need my number line to put my intervals on, my boundary points. I end up with a +2 and a +7. The +7 comes from the numerator, so it's a value of 0. The +2 comes from the denominator, so it's a place where the function is undefined. I pick a test point in each of those intervals. I chose 0, 5, and 10. You can choose other values. When you test points in those intervals, this is the pattern that you should get. And you are interested in places where your function, your inequality, is less than or equal to 2. So I'm interested in those ends. So from -infinity up to 2, can't include that because the function is undefined there. Or from 7 to +infinity, I do get to include the 7 because the function value is 0 there.